So in this video, we're going to look at how to graph slope fields or direction fields. And a slope field or a direction field, they're basically the same thing, is a way of visualizing the results of a differential equation. So if you have a differential equation, you can, at each point in space, plot the slope that derivative is telling you how to behave at that particular location, at that combination of x and y or x and t. And so we have some examples here of direction fields that have been previously plotted. So in this case, this is actually an example of essentially an autonomous differential equation where the horizontal axis actually has the same slope for every value of y. It's only the y value that's changing the direction of the slope. And again, at each point in space, we're essentially plugging in the coordinates into our differential equation and determining that angle, that direction of the slope. In this case, this is a direction field that depends on both x and y, or both y and t. And so you can see that it's not the same slope going all the way across. The value of the slope actually depends on both of the coordinates. And what we're going to do is we're going to see that we can actually use this slope field in order to determine the sort of general behavior of a differential equation without actually having to solve it explicitly. Sometimes differential equations are easily solved, and sometimes they are very, very difficult to solve. And so this gives us a way of sort of characterizing the quality of the behavior, the different kinds of trajectories that the solution can produce without actually having to solve that equation explicitly. So let's look at a particular example with an autonomous differential equation. An autonomous differential equation is an equation where we have the derivative and it's equal to just properties of the function itself. So again, there's no explicit appearance of x or t in our equation. So an example would be something like y prime is equal to y plus 2. This does not have to be linear to be autonomous, but for the sake of simplicity, I decided to start with a nice simple linear one. Now, if we wanted to plot this slope field by hand, we would basically choose a point in space, and then we would plug it into the differential equation to obtain the slope. So for instance, if I start with y equals 0, I would plug in y equals 0 here, and I would get a slope of 2. So then I would attempt to plot on my graph for y equals 0 the equivalent of a slope equal to 2. Now, I'm really only concerned with essentially the direction. There's no length to this, so all I have to worry about is that it is essentially going to be at a steeper angle than, let's say, y equals 1, for the slope equal to 1. If I plug in y equals -1 into the same equation, then I get a slope of 1. And so on the y equals -1 line, I'm going to plot a slope of 1, so that 45-degree angle. And because this is autonomous, the slope doesn't depend on that second variable, so it's going to be the same all the way across. So once I find it at one point in an autonomous equation, I can just carry it all the way over. If I continue plotting points when y is equal to -2, I get 0. And so that's going to be a horizontal slope. And so then I can keep going. If I plug in y equals -3, I get a slope of -1. That goes all the way across. And then a slope, if I plug in -4, I get a slope of -2. And so again, it's steeper, but still negative as I go all the way across. So again, this is the idea here, is that this is going to give me some idea about the behavior of the system. Now, how would we interpret this in terms of its behavior? Well, if I have an initial condition that starts me right here on the graph at y equals -1, then this is saying increase in value as you go forward in time. And so I would go in this general direction until I would hit a new slope. And as I go forward in time, because my y value is increasing, my slope will also end up increasing. And so I will end up with this kind of exponential behavior. On the other hand, if I start at exactly y equals -2, then the slope is always 0. And so I'm just going to travel along horizontally, remaining that same value all the way across the graph. Now, we can plot this on a much larger graph using technology. We can fill in the entire field at a much greater specificity of values. And we can then use the entire slope field to, again, sort of observe the behavior of the system as we go through time, as we start at some particular point. We try to follow the slopes as they go. And this, if we start here, for instance, it will tend to go up to the right. And the further we go, the steeper that slope is going to be. If we start below this horizontal line, then the slopes will be pointing downward. And so we will go downward. And again, as we get further away from the line, the slopes will get more vertical. And so it will take us more steeply away from that line. This point where the slopes are horizontal, we call that an equilibrium point, because if you start there, you stay there. Now, often we don't really want to fill in the entire slope field. We just want sort of the general behavior of the slope field. And so when we do that, particularly when we're graphing it by hand, we're going to start always with this equilibrium value. And the equilibrium value occurs when the derivative is equal to 0. So for our example, we would set the derivative dy dx equal to 0, and we would have 0 is equal to y plus 2. And that would give us the equilibrium at y equals -2. And so that's a horizontal trajectory. If you start there, you stay there because the slope is 0. But then what we can do is we can test the sign of the slope field on either side of that equilibrium solution. If we plug in y equals -3, we get a negative slope. And if we plug in something above that, every value above that is going to give us a positive slope. And so when you're very close to the y equals -2 line, you're going to be increasing very slowly if you're above it and decreasing very slowly if you're below it. But as you get further and further away, that slope will become steeper. And so you'll get this exponential shaped curve approaching that equilibrium point. Now, in this particular case, this equilibrium point is called a repeller because both of the trajectories pull away from this equilibrium solution. So it's unstable. Now, we can never cross the equilibrium point in an autonomous equation like this. And so we can always be clear that once you're on one side of the graph or the other, you're going to stay there. It's just a question of, are you getting closer to the equilibrium or are you getting further away from it? Now, there are essentially three kinds of solutions we can expect in an autonomous system. If the solution is unstable, as we saw in the previous case, it's referred to as a repeller. In population dynamics, if this is a position that is above 0, it's also sometimes referred to as a threshold. Stable solutions are sometimes referred to as attractors, and this occurs when the trajectories are all heading toward the equilibrium position, so they're negative above and positive below instead of the reverse for the repeller. We can also have a semi-stable solution. You can think of it like a saddle point. In this case, this typically occurs when you have something like a factor in your equation that is repeated. So it's going to come down to be 0 at that point, but then it's going to stay the same slope, the same sign on either side of the solution. So what you will have is you will have on one side of the graph, the trajectory will approach the equilibrium, and on the other side of the graph, it will go away from it. So it'll either be positive on both sides or it'll be negative on both sides. And so that's called a semi-stable solution. It's stable from one direction, but not from the other. So I want to look at another example of a slightly more complex autonomous equation, and then we'll look at the non-autonomous case. Now, when you have an autonomous equation, such as this one, sometimes it can be helpful to graph it as if it were a function in order to determine the signs and the intercepts for our equilibrium position. So here I've graphed our differential equation y squared times y squared minus 4, and we can see that we have intercepts at -2, 0, and 2. So those are going to be our equilibrium positions. Those are the positions where where the derivative is equal to 0. In this graph, x is our y variable, and the y-axis is our dy dx variable. And then we can also see from this graph that it's going to be positive, then negative, and it's going to stay negative, and then it's going to be positive on the outside. So when we transfer this is sometimes referred to as a phase plane, we can transfer this sign information to our actual slope field. So we're first going to take our slope field. We don't really care about time equals negative values, so we're going to leave that off the graph. And we're going to plot our equilibrium solution. So we have one at y equals -2, one at y equals 0, and we have another one at y equals 2. And then we're going to add to this graph the sign information that we got from the phase plane. So up here where we were looking at values that are less than -2, the graph is positive, then we'll translate that here into a positive slope. And again, here we're just looking at the general direction, not the exact values. And then it's negative in between. And then on the outside, when you get above 2, then our graph was positive again. So these are the, again, general properties of our slopes. And if we keep in mind the fact that as you get closer to the horizontal, the slopes will become, these horizontal lines, the slopes will become shallower. And as you get further away from them, the slopes will become more steep, as we saw when we actually filled out the whole direction field. Then what you get is behavior that looks like this. So when the slope is positive, it's increasing. As it gets closer to that line y equals -2, it can't cross it. So the slopes remain positive, but they get shallower. When you're above it, you start close to 0, and then you decrease the fastest when you're actually in the middle of these two equilibria. And then when you start getting closer to that y equals -2 line, again, you shallow out. The curve is basically going to look exactly the same in the region of between 2 and 0, because the slope is pointing in the same direction and has that same bounding conditions. This type of curve that you see in between equilibria like this are sometimes referred to as logistic curves. And then they're kind of S-shaped curves. And then when you get above the y equals 2 line, then again, you start out close to y equals 2. The slope is very shallow, but the further you get away, the more steeply it goes. And so you end up with this essentially exponential curve once you get above that y equals 2 line. So we didn't have to actually plot out this entire slope field in order to get the sense of the behavior of the solutions to the differential equation. We essentially have 4 different types of solutions to our differential equation. And if you actually plot out the entire slope field using technology, then our slope field is actually consistent with what we got here. And again, we could follow these curves and we could see, like here, these are negative and then they get shallower. And again, you can't cross the equilibrium. And so especially if we were to fill in additional detail, it would be very clear that this is how our trajectories would have to behave. Now, in this example, we have one stable equilibrium, which is the one at y equals -2. We have one unstable equilibrium at y equals +2, and then we have a semi-stable equilibrium at y equals 0. And the y equals 0 one occurs because in our original differential equation, that was a repeated root. And so you can see from the phase plane, it bounces off the 0. So it doesn't cross over and change sign. And that's what happens when you get a semi-stable equilibrium. Now, let's look at an example where we do not have an autonomous equation and we have to, we can still sort of, without technology, sort of, if we're careful, plot out the general behavior of the system without having to like fill in literally every point in the plane the way that technology will for us. It's also going to depend on setting our derivatives equal to 0. Now, in this case, again, rather than plotting every point. So if I set my derivative here equal to 0, since this is my differential equation, what I'm going to get is there is a line of horizontal tangents when y is equal to -2t. So t is on my horizontal axis, y is on my vertical axis. So if I plot this line, then I can put these horizontal axes, these horizontal slopes directly on top of this line. Anytime I pick a pair of y and t values that are that have this relationship, I'm going to get 0 in my differential equation. And so that means it's going to get me a horizontal slope. Now, this is essentially going to divide up the plane into a couple of different regions. And so what I can do then is I can use my axes and this y equals 0 or the y prime equals 0 line in order to choose a couple of key points in order to understand what the behavior of the field is doing. And so what I've done is I've selected a couple of points that are scattered around the graph in order to understand what's happening. So if I take the point -3, 2, so -3, 2, that's going to be here. I'm going to plug that into my differential equation, which was 2t plus y divided by 2y. And what I'm going to end up with is a slope of 1. So it's positive, pointing up to the right. And if I plug in the -3, -2, which is this guy down here, into that same equation, I'm going to end up with a slope of -2. Again, the exact slope is not really as important when we're just kind of eyeballing it. But we do need the sort of general direction. Is it positive or negative? Is it up to the right or down to the right? When I plug in the point 0, 2, that's right here, then I'm going to get another negative slope. And when I plug in the point 2, 5, which is this guy up here, this is also a negative slope. And then when I plug in the point 2, -2, that's down here, I'm going to get a positive slope. So what I can kind of see is if I'm starting here, I'm kind of going increasing here, and then I'm going horizontal, and then I'm going back down again. Now, if we go back to my original differential equation, there is a y in the denominator. So when I get to y equals 0, I'm going to end up with an undefined slope, which means it's going to be vertical. And vertical tangents can sometimes create problems for us. But we can then, this will sort of give us a general idea of what's going on, particularly as we develop more experience with these kinds of slope fields. But I can confirm that this is a general behavior by plugging this into technology. And this is what I get when I plug it into technology. If you look very carefully, you can see there are these horizontal slopes that have this y equals -2t line, and that the slopes do in fact go vertical at y equals 0. And so they're kind of spinning around the graph like this. Now, of course, our differential equations are actually going to cease to be a particular solution the moment that they go vertical. So you're not actually going to necessarily get swirling behavior. The solution will actually become undefined and then just kind of stop at that point. Now, there are lots of direction fields out there. This one may no longer be working because I wrote this quite some time ago. But if you Google for direction field grapher or slope field grapher, there are lots of examples out there you can use to use technology to draw your slope fields and to sort of get a sense of how they behave. A lot of them will also plot trajectories for you. So if you put a point on the graph, it will show you where that plot would go, either forward in time, or also in many cases where it would go if it was approaching that point. It was just a curve passing through that point. So where it would go backwards in time.